Okay, so just a minute ago, somebody asked a wonderful question. And the question was, what would you do if you had a differential equation and you had tangent over here? I think the person asked tangent squared, but tangent has the same problem as tangent squared. What would you make for a guess for your y sub p? Secant, all right. The problem with guessing secant x is what happens when you take the derivative. And it would be a, there'd be an a in front, right? The derivative of secant is secant x tangent x.
I got your tan again.
And I have my tan again, but unfortunately my tan is being multiplied by a secant. I'm not going to have anything to equate that with on the right hand side. And then when I go to take the second derivative, now I got to use the product rule. It's going to get pretty nasty, isn't it? And we're not going to have the right things to be able to equate on both sides. Not going to work. So then what? Call for help. All right. And the reality is, this is a good example, the method of undetermined coefficients doesn't always work. And this example right here is an excellent example. It doesn't work because we don't have anything that we can make a guess. We haven't seen any differential equations where tangent turns out to be the solution. Our solutions have always been polynomials, or they've been sines and cosines, or they've been e to powers. We haven't had any differential equations where tangent is the answer. So we don't have any good guess to make. It's just not going to work. So what you do is you use a different method, which is called variation of parameters. This method works more often, but can be more difficult to do. The way it works is you have a nice long formula. Y sub p is minus y1 times the integral of y sub 2 times f of x divided by the Wronskian of y1 and y2.
Where did they get this?
Dx. Well, it's all derived in your book. I'm not going to bother going through the entire derivation. Plus, it's not done yet. Plus y2 times the integral of y1 times f of x divided by the Wronskian of y1 and y2 dx. Where? What are this y1 and this y2 that I wrote down? Not particular solutions. They're the C solutions, which are come from your characteristic polynomial, where y sub c is y1 plus y2. So y1 and y2 are the solutions from your characteristic polynomial. And what's this f of x? Well, for this example up here, f of x would be tangent. It would be this function over here. All right, so let's try that for this differential equation. Y double prime plus y equals tangent x. The first thing we need to do is we need to solve the complementary homogeneous equations. We need to solve y double prime plus y equals 0 to find our y1 and our y2. How do you solve that equation? R squared plus r, or r squared plus 1 equals 0. So r is plus or minus I, which means my complementary solution is C1 cosine x plus C2 sine x. So wherever I see y sub 1, I'm going to use cosine x. Wherever I see y sub 2, I need sine x. The other thing I need is I need the Wronskian of those two functions. So we might as well just work that out. The Wronskian is, I'm going to have a cosine x and a sine x. The derivative of cosine is negative sine, and the derivative of sine is cosine. Find the determinant. I multiply cosine times cosine is cosine squared x, and then minus negative sine times sine becomes a plus sine squared. Oh, that one comes out very nice, doesn't it? Turns out to be the number 1. Isn't that convenient? Isn't that convenient?
That means it's linearly independent.
That means they are linearly independent. That is correct. Because if they were linearly dependent, I wouldn't have got the number 1. I would have gotten 0. So those two functions are linearly independent, which we already knew from previous work. All right. So to find y sub p, basically I have to be able to compute two integrals. Is this method of variation of parameters always going to work? No, because sometimes you may not be able to compute these integrals. Depends on the functions, depends on how things turn out. So this method doesn't always work either. But it works more often than the method of undetermined coefficients.
So is there a way to solve them every single time?
Not that I'm aware of, no.
I just want to know this is as bad as it gets.
This is as bad as it's going to get for this class. Okay, so what I'm going to do, I'm going to do the two integrals separately. I might as well just figure out the integrals, and then I'll multiply by the things I need. So the first integral, I need y sub 2. Y sub 2 was sine x. And I multiply by f of x, which was tangent x, dx. How do you integrate sine x times tangent x? It turns into sine x?
Yeah, because tangent is sine over.
What's that? Where did it come from? I'm working out this integral right here. So y sub 2, that's sine x. F of x was this function over here, that's tangent x. And I divide by the Wronskian, but we determined that the Wronskian was the number 1. So that's handy.
Integration by parts, right?
Integration by parts?
Can you make it sine squared over cosine and then u substitution?
Can I make it sine squared over cosine and then make it u substitution?
Yes, we can.
Okay. I completely agree that that is sine squared x over cosine x, because tangent is sine over cosine. U substitution, what are you going to let u be? Sine squared, what's the derivative of sine squared? You don't get 1 over cosine, do you? So that u substitution isn't going to work.
Wait, can you split it up so it's like sine over cosine times 1 over cosine?
That would be sine over cosine times sine,
Which is
right back where we were. Other good ideas. Trig substitution. No, you don't use trig substitution when you have trig functions. When do you use trig substitution? When you don't have trig functions. What do you have? You have square roots with squares involved. We certainly don't have that.
So
Not the power reduction formula.
Is that where you make the table and you go down and do your derivative and you go down to your integral?
No, that would be integration by parts by the tabular method.
man, Calc 2 was so long ago, I can't remember.
All right, so I'm going to recommend that all of you show up to my Calc 2 class on Monday when we cover integrating powers of trig.
Wow.
How about taking sine squared and writing it as 1 minus cosine squared? That's too easy. That was no fun. And then 1 divided by cosine is secant. So this becomes the integral of secant x minus cosine squared over cosine, that's cosine x. The integral of secant is, that's the derivative of secant. I want the integral of secant.
Cosecant squared, negative cosecant squared is
It's one of those.
It's what the natural log is. It's the natural log of
secant u.
The integral of secant is the natural log of the secant plus tangent. And how about the integral of cosine? Sine, but we already have a minus, so that's going to be minus sine. No, we don't want plus c because remember this is going to be part of this big formula up here, which is going to be part of our particular solution. So we don't want a plus c here. We don't want numbers involved. So what we would have to do now, that's right, when we get all done, we've got to take this answer and we've got to multiply it by negative y1, which is negative cosine. But while we're here, we might as well also compute that integral. Might as well, because we got to do it anyway. All right, so that's going to be the integral of y1, which was cosine x, times f of x, which was tangent x, divided by the Wronskian, but the Wronskian was the number 1. We liked that a lot, dx. That happens to be the integral of sine. This is the easy one. That's the integral of sine x, which is negative cosine x. Okay, so our particular solution, y sub p, it was, gotta go back and look at the formula, negative y1 times the first integral that we figured out. So negative y1, that's negative cosine x, times the first integral we figured out. That was ln of secant x plus tangent x minus sine x, I believe is what we had. And then we need plus y sub 2 is sine x, times the second integral that we figured out, which we liked a lot more because that was the easy one, negative cosine x. So there is your particular solution to y double prime plus y equals tangent x.
So if you want to take the derivative and the second derivative of that, that'd be fun.
If you wanted to take the derivative and the second derivative to check and make sure it works, that would be a lot of fun. I agree. Max.
So where did y1 and y2 come from?
y1 and y2 came from the solution of the homogeneous equation. So this one is y. Well, I called this one y1 and I called that one y2. You could, of course, switch them. The order that you write them in doesn't matter, but usually when we write these, we put the cosine first and the sine second. I don't know why, but that's the way we normally write them. So there's your y1, there's your y2.
All right.
Other questions? Seven.
On the particular solution, the sine x cosine x will cancel out.
What he is saying is, if I took this negative cosine x and distributed it through, it would add up to 0 when combined with that one. That is correct. So he's saying you could simplify your solution to be negative cosine x times ln secant x plus tangent x. Absolutely. You would have stopped one line above. Yeah.
Because if you ask us one of those questions, that's all you're looking for.
Correct. If I ask you one of these questions, that's what I'm expecting for a final answer. If you go ahead and simplify it, that's fine. Just simplify a little bit.
Okay.
Other questions? Is this method easier than the method of undetermined coefficients? The correct answer is sometimes yes, sometimes no. It all depends on how complicated these integrals turn out to be. If one of them had turned out to be the integral of sine and the other one just turned out to be the integral of cosine, I think you would have said this method's a lot easier. There's no way of knowing when you go to start the problem which one's going to be easier. Sometimes the method of undetermined coefficients is easier. Sometimes the method of variation of parameters is easier.
So in the test, are you going to tell us in the instructions which method to use, or should we just...
I will not. It will be up to you to decide which method to use.
Okay.
And I have had students who choose to do every problem using this method. It works. That way they only got to learn one way and they know it's going to work for all the problems I'm going to give them on the test.
Now, can we do it one way and then the other way to check?
Absolutely, if you have enough time. How's the test going to be? Long and hard and lots of questions. That's the obvious. To answer that question, I'm going to pass out a sheet.